Hey, everybody, welcome back. Hope everyone had a good week. Let's see, we just got done with last Friday, we got done with chapter 12. We have a limited number of weeks left over, I guess 5-6 weeks. We have a limited number of chapters. So basically for the next Friday, I mentioned this, we'll probably be doing a chapter and a half, and then save the other half of the time for any questions that you may have. If there are any questions, I mean, what I like to do today, unless you have questions, we can stop and answer them. If not, I'd like to continue with chapter 13. It's also a short chapter. And then after we're done with that, take a little short break, then go back and work through some of the problems in the worksheet for chapter 12 and 13. Okay. So any questions or something that needs to be addressed before we begin? All right, well, let us begin then.
I have a quick question, Dr. Fred.
Sure, you go right ahead.
So I started the lab like an hour ago, and I'm still kind of working through it. So is it okay if I mute this, and as soon as I'm finished that, just jump back on to this lecture?
Yeah, sure. In fact, the lab itself stays open for, you can come back to it. It won't kick you out. So you can jump out of it and then come back to it whenever you're ready.
Oh, okay. I might just leave it in the background, just like ticking on time. Okay.
That'll work too.
Okay, cool. Thank you.
Yeah, sure, no problem. All right, any other questions? Yeah, this semester is going pretty quick. Really flies through. All right, so let's do chapter 13 now. Chapter 13 has the name called Stoichiometry. Okay, big old fancy name, word I should say. And what it is real straightforward. You're already familiar with stoichiometry in your everyday life, if you think about it. For example, we all have, if you have a vehicle, four-wheel vehicle, you know that a vehicle requires 4 tires. So the stoichiometric relationship between a vehicle and a tire, and tires would be a 4-to-1 ratio, right? We need 4 tires. Unless you got a motorcycle, then it's a 2-to-1. And if you got a tricycle, it's, it's a 3-to-1 relationship. That relationship is a stoichiometric relationship. Now, we have been balancing equations. We started with the 6 different types of equations, and then we discussed how to balance, each one. The first couple, we do a trial and error, but then for the other ones, for example, the combustion reaction, we had a set system where you balance the carbons, hydrogens, and oxygens, etc. Once you balance that chemical reaction, and that is because the laws of conservation of matter dictates to us that if we start off with 6 carbon atoms as a reactant, then when it's done doing whatever it's doing, you're going to end up with 6 carbon atoms. Now, of course, they're going to be in different forms, right? And so, but we have to balance it. And those numbers in front of those coefficients in front of the compounds, that is the stoichiometric relationship between the reactants and the products, okay? A lot of times, a majority of reactions is a real straightforward 1-to-1. I need 1 of A to give me 1 of B, plus 1 of B gives me whatever I'm going to get product-wise. But it's not always that case. Sometimes it's a 1-to-2 or 1-to-3. It's even could be a 3-to-2 or a 2-to-3, whichever the ratio dictates that we need that number to balance the overall reaction. And those stoichiometric relationships we can utilize as a ratio, okay? As a ratio. So let's take, for example, this particular reaction. We have nitrogen monoxide in the presence of oxygen reacts to give us nitrogen dioxide, okay? So we balance it. We see we have 2 nitrogens on the left, 2 nitrogens on the right. We have a total of 4 oxygens as reactants and 4 oxygens as products, okay? So what we can say with those coefficients is we can say, well, it takes 2 molecules of NO to react with 1 molecule of O2 to give us 2 molecules of NO2, okay? Now, if for whatever reason we boost it up and we utilize 10 molecules of NO, well, we have to maintain that 2-to-1 ratio. Notice it's a 2-to-1 ratio of NO to O. You know, it's understood that that's a 1. So there's a 2-to-1 ratio here. And so therefore, if we up the NO, nitrogen monoxide, to 10 molecules, well, based on the ratio of 2-to-1, we require 5 molecules of O2, okay? Which then gives us 10 molecules of NO2, nitrogen dioxide. The relationship is of 2 to 1 to 2 is maintained regardless of the numbers we utilize. And this relationship is true whether we utilize 10 molecules or we utilize 10 moles. Remember, 1 mole is equal to 6.02 times 10 to the 23rd. You know, in this case, you know, it could be molecules, okay? And so this reaction can also read 2 moles of NO require 1 mole of oxygen to give us 2 moles of nitrogen dioxide, okay? Excuse me, let me clear this up. Now, this relationship between the reactants is a ratio. So we could write 2NO over 1 oxygen as 1 ratio, or we can invert that, okay, and write O2 in the numerator and 2NO in the denominator. And that's just between the reactants. But I could do the same thing with respect to one of the reactants and the products, where you can see that there is 2NO per 2NO2. And I can write it like that or invert it, okay? Now, which by doing this allows me to, you know, going back to how we did conversion factors, where we converted units from English to metric and metric to English, or even the units within the system that we're working with. You know, we keep track of our units. And so, for example, if the question says, if I have 100 moles of oxygen, okay, how many moles of NO do I need? Okay, so that's the question. And so I see the relationship, I look for the relationship between oxygen and nitrogen monoxide, which happens to be the 2-to-1. So I'm gonna use either this one or this one. Okay, but then I look at the question, it's asking, I'm looking for moles of NO. So obviously I'm going to use the first one because I want oxygens to cancel out. I'm looking for nitrogen. So I'm using that relationship of 2-to-1 with nitrogen monoxide in the numerator. Keeping track of my units, you could see O2's cancel. Now 100 times 2, obviously I need 200 moles of NO. If I start off with 100 moles of oxygen, okay? All right. Another reaction, for example, we have nitrogen in the presence of hydrogen gas gives us ammonia, NH2, okay? Again, it's understood to be a 1 here, okay? We don't have to write the 1, but it's understood to be a 1. So it says that 1 molecule of nitrogen requires, at the minimum, 3 molecules of hydrogen gas to give us 2 molecules of ammonia, NH2, okay? Now, obviously, we're not working in the real world, so to speak. We're not dealing with just molecules. We're dealing with large quantities. We're working with moles. And so here, we can substitute the molecule and use the term mole. Okay, so 1 mole of nitrogen requires 3 moles of of an hydrogen gas to give us 2 moles of ammonia, okay? And then we have, once we balanced it, we had that relationship between 1 nitrogen over 3 hydrogens, for example, or invert it, 3 hydrogens over 1 nitrogen. And that's just simply between the reactants. But remember, we can also utilize the relationship between one of the reactants and the product. So between nitrogen and ammonia, or between hydrogen and ammonia. Okay, because a lot of times, let's say, you know, you're working out in the industry someplace and you are required to make, let's say, ammonia. And so you might have the project of making, I don't know, 1 million pounds of ammonia. Okay, starting with hydrogen and nitrogen. 1 million pounds, or let's say 1 million kilograms. Okay. Well, whether I make so I can use that relationship, I need to ask the question, if I need 1 million kilograms of ammonia, how many kilograms of nitrogen do I need? Okay. And I still use this relationship between nitrogen and ammonia. And we're going to have some examples of those calculations. Okay. And this relationship of 1 to 2, or whatever relationship it is from the based on the balanced chemical equation, is true whether we're dealing with units of kilograms in the lab, or we are dealing with tons, metric tons out in the industry. That ratio is the same. Many a time I had to calculate how much of this a product I need to make based on the reactants and the amounts of the reactants. And we have a balanced chemical equation, and we have the molar mass, and we can calculate. Okay. All right. So coefficients gives us the mole ratios between the reactants and products, and also within products. You may have more than one product. In both cases here, we have one product, but sometimes you may end up with 2 products. And there's a mole ratio between the 2 products too that you utilize. Okay, so let's take this example of this reaction. Okay, question number 1. Can anybody tell me the name of this compound?
Is it iron oxide?
Okay, that's 50% correct. You got it. Okay, how about let's work on the other half.
Iron oxide.
Okay, we got 2 iron oxides. That's correct also, but 50%.
Is it iron 3 oxide?
You got it, 100%. Iron 3 oxide. Remember that there's 16 metals. You remember the sweet 16, as I call them, group 1, group 2 metals, that we know exactly their oxidation number, their charge. And then we added 4 more. We had aluminum, zinc, silver, and cadmium. So that's a total of 16. Those guys have a constant oxidation number when they become ions. Okay. So therefore, we don't have to use Roman numerals. That means that all the other metals, minus the 16, to differentiate between the 2, we have to use Roman numerals. So this is iron 2 oxide. Also remembering that when they combine, when the iron combines with the oxygen, they have to combine such that they end up with a net 0. Now the oxides, we know each one is a -2, okay? And there are 3 of them. And the whole thing comes to 0. But we also know that there are 2 irons. Okay, so we can generate a very quick, simple algebraic equation where we have 2 irons minus 6 equals 0, because each oxide is a -2 and there are 3 of them, so we get a total of -6. So we solve for iron, and iron becomes a +3. So under this structure here, this is iron give it a name, it would be iron Roman numeral 3 oxide. Okay, because there's another iron oxide compound. Okay, they both share the name, but it is an iron 2 oxide, and that formula is simply FeO. Okay, we know again that each oxygen oxide is a -2. That infers that this must be an iron 2. So we have to remember to use Roman numerals to distinguish between the metals that are not the 16. The ones that are 16, we don't use Roman numerals. So this, for example, is simply sodium chloride, okay? Or this is simply calcium chloride. We don't have to use Roman numerals because calcium is a group 2. All right, so that is correct. And that's why I said 50%, because the other 50% is the Roman numeral. Okay, good. So what this says there is that iron 3 oxide. Now, the other thing to help you out, if you recall, go back and refresh your memory. When I look at this formula, we just calculated that we are utilizing iron 3, okay? And we said that oxygen is a -2. Well, by looking at the formula, way back when I said, think about this. The subscript of the anion, which is the 3, is the oxidation number of the iron. And the subscript on the cation is the oxidation number of the anion, okay? So you could, by looking at just the formula, very quickly identify that it's iron 3 oxide by looking at the subscript of the oxygen, okay? Over here in this case, where we had the other iron oxide, well, there's no subscript, but you know that it's a -2 for the oxide. So that means you're using iron 2 in that case. All right, enough of that, just a quick refresher on nomenclature. All right, so iron 3 oxide in the presence of carbon monoxide undergoes the reaction to give you 2 irons and 3 carbon dioxides, okay? So basically, this is a good way to get rid of rust, because iron 3 oxide, AKA rust, and if you react that with carbon monoxide, you get rid of this rust, you make iron, and unfortunately, you make carbon dioxide. All right, now, that's the balanced chemical equation, and we can write ratios between the 2 reactants, where I got a 1 iron 3 oxide over 3 carbon monoxide, or I can invert it, okay? So that's the relationship between the 2 reactants, okay? So now the next one here, that relationship is between the iron and the carbon monoxide. So basically I can have 2 ratios for that relationship, okay? And now I not only do I have a relationship between 2 reactants, I can also have a relationship between stoichiometric relationship between the iron 3 oxide and the iron. So that is a 1 to 2, or I can invert it or use that relationship, okay? The bottom line is this. And then between carbon monoxide and carbon dioxide. So there's 2 more. So I got 2, 4, 6, and then between the 2 products, the 2 to 3 relationship. So I got a total of what? 6 relationships, right? Here, let me clear this up, and I'll start with this color. So between the 2 reactants, okay? between iron 3 oxide and iron. So there's 2 right there, 2 more ratios. There's 2 here. And then between the iron 3 oxide and carbon dioxide. So there's 2 more right there. Okay. And we change the color here. And then between carbon monoxide and iron, that relationship, there's 2 ratios there. And then carbon monoxide and carbon dioxide, there's 2 ratios there. So I got 2, 4, 6, 8, 10 ratios already. And then finally, 12, because the relationship between 2 to 3 between the two products, okay? So I got a potential of 12 ratios that I can utilize. And depending on which one I use depends on the question. Now, when it comes to the question and to figure out which ratio you need, you have to read the question carefully, okay? And you only have to deal with what the question is asking for. For example, the question says here, how many moles of iron can be formed from 10.2 moles of carbon monoxide? So the relationship one is concerned about is simply between iron and carbon monoxide. Okay, we don't care about all the others, simply between iron and carbon monoxide, which turns out to be 3 carbon monoxide over 2 iron, okay? Or invert it, 2 iron over 3 carbon monoxide, okay? That is our stoichiometric relationship, our ratios. The question is, which one do we utilize? Top one or left one? Well, to answer that depends on the question. As any of the problems we've been doing before, first step, you write down what you're given, right? 10.02 moles of carbon monoxide. Obviously, we're going to need a conversion factor here at some point, but what are we looking for? We are looking for moles of iron. So that means that I need iron in the numerator for this ratio and carbon dioxide in the denominator, right? Because I want carbon monoxide, excuse me, I want those to cancel. Well, obviously I need to use the bottom ratio. So it's 3 to 2, and you got it set up. So see, even way back when we were talking about conversion of units, I said, follow your units, set your units up properly, okay? And follow them through, cancel things too, and you got the problem set up. You will have the problem set up properly, okay? And so here, we just went through the exercise and I wrote it all out for you. So eventually you get to the point where you become comfortable with not having to write it all out. But in the beginning, write it all out until you're at that point. So that's why I wrote out the ratios out there. So I'm aware of which ratios I need to work with. I'm only concerned about the iron and the carbon monoxide based on the question. Don't care about what's happening to carbon dioxide or iron 3 oxide because the question has nothing, asks nothing about it, okay? Once I do that, I got my ratio between the 2 parties of interest. I got it right here. I go back and write down what I'm given, 10.2 moles of carbon monoxide. I write down what units I'm looking for, which is moles of iron, which then tells me which of these 2 ratios I need to utilize, okay? And if you go through that systematic approach, and after doing these for a period of time, you get to the point where you don't need to do your systematic approach. I equate that to riding a bicycle. Very few people that I'm aware that the first time they ever seen a bicycle, they jumped on it and they're going down the road with no hands on the handlebar. You know, it took a while for the most of us that we get on that bike and we're, you know, bouncing all over the place and crashing until we got to the point that we can ride that bicycle without using the handlebars, holding on to the handlebars. You know, it took a while, but it took practice, okay? And here I'm presenting a systematic approach for these problems. And then with time, you can work them through your direction, whatever works best for you. Okay, so let's look at the answer here. Yeah, we know that. And so notice here we have 6.8 moles of iron. It's been set up so that carbon monoxide, they cancel out, leaving us with units of iron. Okay, so what that says is if I start off with 10.2 moles of carbon monoxide, okay, and I have sufficient amount of iron 3 oxide, that's the assumption that you have sufficient of that once the reaction is done, I will end up with 6.8 moles of iron. Okay. Now, keep note of this, keep this in the back of your head. In the lab, we don't measure out in moles, we measure out in grams. And so since we're working with moles right now, the next logical step would be to convert those moles to, guess what? Grams. And to do that, we need the molar mass or the atomic weight of whatever species we're trying to calculate. Okay, so the next logical step for here was to convert, will be to convert the 6.8 moles of iron to, guess what? Grams of iron, because that is what you would actually measure, grams, not moles. All right, next question says, how many moles of iron 3 oxide are needed to form 17 moles of carbon dioxide? So what we are concerned about based on the question are 1, carbon dioxide and iron 3 oxide. We're only concerned about that relationship. Okay, we're not concerned about the other because we assume that there's sufficient carbon monoxide for this process to occur. And so the relationship between the iron 3 oxide and carbon dioxide is a 1:3. That is the stoichiometric relationship. So what do? We write down what we're given, which is 17 moles of carbon dioxide. That's what we need to make. We need to form that much. Okay. And we have a conversion factor there, and we're looking for moles of iron 3 oxide. Okay, so that tells us that we need iron 3 oxide in the numerator and carbon dioxide in the denominator. So going to the balanced chemical equation and looking at the coefficients, it's 3 carbon dioxide and 1 iron 3 oxide. Okay, so now double check your units. CO2's cancel, which is what we're looking to happen. And now it's a matter of doing your math. 17 divided by 3 should give you 5.7 moles of iron 3 oxide. So another way to say this is, here's an example where you're trying to calculate how much of one of the products you need to make for whatever reason. And I need to make 17 moles of carbon dioxide. Okay, 17 moles. With that information, given that we have an excess of carbon dioxide, I need to calculate how many moles of iron 3 oxide do I need to begin with to make that amount of carbon dioxide. Okay, and we need 5.7 moles. Any questions right now at this point? All right, so here's an example where we got to balance this equation. So we have sulfur dioxide in the presence of oxygen to give us sulfur trioxide. And so to balance this, we require 2 SO2 sulfur dioxide, 1 oxygen, okay? And that results in giving us 2 moles of sulfur trioxide. All right. First question says, how many moles of sulfur trioxide will form if we begin with 0.165 moles of oxygen? Okay. And so our only concern is the relationship between oxygen and sulfur dioxide. So if we begin with 0.165 moles of oxygen, how many moles of sulfur dioxide will be created? Okay, so like we've been doing, write down what you're given. So we are given 0.165 moles of O2, okay? And we are looking for moles of sulfur trioxide. That now knowing where I'm starting, what I'm given, knowing unit-wise where I got to go with, then helps me to determine how to set up my conversion factor. Since I'm looking for SO3, sulfur trioxide, obviously that belongs in the numerator, and sulfur and oxygen belongs in the denominator. Okay, I go to the balanced chemical equation, the coefficients 2 SO3s per 1 oxygen. Okay, so that is our stoichiometric relationship. And it's not, double check your units. O2's cancel. We're good to go, leaving us with units of sulfur trioxide. So do the math, 0.165 times 2 results in 0.33 moles of sulfur trioxide. So if I begin with 0.165 moles of oxygen, I would make 0.330, that's a 3 moles of sulfur trioxide. Okay. Now, up to this point, we've been dealing with 1 mole, 2 moles, whole numbers. But in the real world, we're not really dealing with whole numbers. We're dealing with quarter moles or, fractional moles. Here we go, 0.165 moles of O2. Okay. But regardless of it being fractional moles or whole moles, that ratio, that stoichiometric relationship remains the same. That doesn't change. Okay, question number 2. How many moles of sulfur dioxide? And so we're looking at the dioxide are needed to make 0.042 moles of sulfur trioxide. So what we are concerned about is the relationship between sulfur dioxide and sulfur trioxide. Now, you might see something here that can help you answer that question real quick, but we'll see if you recognize what I'm talking about. But let's work the problem out like we normally do. So we start off with 0.042 moles of sulfur trioxide. Okay, there is a conversion factor here. We're trying to get to moles of sulfur dioxide. Okay, so obviously the dioxide is the numerator and the trioxide is in the denominator. Going back to the balanced chemical equation, it's a 2 to 2. Okay, check my units. Sulfur trioxide cancels out unit-wise, leaving us with sulfur dioxide, which is what we're looking for with respect to units. And so this turns out to be 0.042 moles. Why? Because 2 over 2 cancels out, right? 2 over 2 cancels out. And so 0.042 moles of sulfur trioxide will generate the same amount of sulfur dioxide, required same amount of sulfur dioxide. Because the stoichiometric relationship between those two is a 2 to 2 relationship, which is simply a 1-to-1. And that's what I meant. If you recognize right away without having to work the problem, that you can see from the balanced chemical equation, it's a 1-to-1 relationship or 2 to 2. 2 to 2, 1-to-1, 3 to 3, 4 to 4, 4 over 4, 100 over 100. That's still 1-to-1, right? because those numbers cancel out in that ratio. Okay. All right. So recall in the last chapter, we did have a flow chart, okay? And I stated in that flow chart that to get from point A to point B, we can't go directly from units of grams to grams. Okay? We could do that if we knew the units of the weights of all the products or reactants that we were being created, but we don't. All we know is at least one of the reactants, or maybe one of the products. And so what we got to do is we got to convert that mass to moles. We can't get from point A to point B without going through moles. Moles is the common factor to get from point A to point B. And so this flow chart kind of breaks it down for you, because if you are given a problem in grams, okay, and like the problems we just did, where let me back it up for a second. We could have we stuck in moles here. Let me erase this. Okay, but the next step, like I said, when we're in moles, the next step is to work in grams, because those are the units that we actually work with in the lab. And so we could, instead of moles, the problem could have been, all right, I got 0.40 grams of sulfur dioxide, okay? How many grams of sulfur trioxide do I need? Earlier, we had talked about moles, but we have to add one more step, because now we're dealing with grams. And with grams, to get 2 moles, we need the molar mass, okay? Or atomic weight, if it's just the element itself. Because from grams to moles, we divide by the molar mass / atomic weight, okay? So moles given, we need the molar mass. And we divide by the molar mass to give us the moles of whatever we've been given to start off with. Now, based on the balanced chemical equation, and the stoichiometric relationship between whatever parties we are concerned about, we utilize the mole ratio to get us from moles of bananas to moles of oranges, okay? And once we know what we're looking for with respect to units in moles, okay, that's what we're looking for in moles, knowing its molar mass of what we're looking for, then we can calculate the number of grams of what we're trying to find, okay? So in both cases here, what you're going to end up in this case here, you're going to end up with at least 3 conversion factors, and I write them here in parentheses. The first one will convert what you're looking for, what you're given, I should say. Normally that is the molar mass, and that first conversion factor gets you into moles of what you're given right here, okay? The next conversion factor comes from the mole ratio, which now converts you into moles at what you're looking for, what you're trying to find. And then the final conversion factor would be the molar mass of what you're trying to find. And that's this step right here. And now you're at grams of whatever you're looking for, grams of find, okay? But you cannot go directly from grams given to grams find. Cannot do that without going through moles, okay? You gotta go through moles. So let me clear up my mess. Okay, so let's look at this reaction here. Here's the other version of iron oxide. This is the iron 2 oxide. Iron 2 oxide in the presence of aluminum, okay, reacts to gives us iron and aluminum oxide. Can anybody tell me what type of reaction this is?
Is it single replacement?
You got it. That's good. It's a single replacement. Okay. Remember, a single replacement, you generally start off with an element, in this case, aluminum, and a compound. Okay. And then what you do is you look at, obviously this reaction proceeds, but if you didn't know what the products were, you look at the activity series of aluminum and compare aluminum with iron. And if you look up the activity series, which is on the periodic table, you'll find that aluminum is a lot more reactive than iron, okay? That being the case, the next question you ask is the most reactive metal, which in this case aluminum, in compound form? And the answer is no, it's in elemental form. Therefore, yes, reaction proceeds. If the most reactive metal was already in compound form, then you get no reaction, okay? And single replacement, because what's happening here is the iron in ionic form. This is ionic form, iron, okay? And here's the other metal in elemental form. Okay, elemental ionic, so the iron and the aluminum exchange places, and now you convert the iron that was in ionic form, now it gets converted to elemental form, and then the aluminum goes to ionic form, ionic compound. Okay, all right. So that's a reaction and that's balance, and so now we can do a series of calculations, okay? So the first question is this. It says, calculate the mass of iron 2 oxide needed to react completely with 5.55 grams of aluminum, okay? And so what I do from my perspective is I write down on the balance chemical equation the principal parties in this reaction, which is 5.5 grams of aluminum, okay? And then we want to know about the iron 2 oxide. So we're only concerned between the two reactants. We want to know how many grams of iron 2 oxide are needed to react completely with 5.55 grams, okay? That's the first question. Then another question, let me change the color a little bit. Calculate the mass of aluminum oxide produced when there are 10.25 grams of aluminum. So our concern, this will be in yellow, will be simply between the aluminum and the aluminum oxide. And in this case, if we start off with 10.25 grams of aluminum, how many grams of aluminum oxide are created? Aluminum oxide, it's a lot of times they use this in sandpapers, very corrosive material. All right, so two separate questions, okay, two separate bits of information, and we can work the problem. All right, so let me clear this up. So the first question was, if we start off with 5.5 grams of aluminum, okay, how many grams of aluminum iron oxide we need? So that's our relationship, okay, between these two here, okay? Plus, note the stoichiometric relationship is the 2 to 3, stoichiometric relationship. All right, so since we're starting off with grams of aluminum, remember, we need to get into moles. Okay, moles. We cannot do anything without first converting to moles. So we need the atomic weight of aluminum, which is 26.98 grams. Okay, and that first conversion factor will get us from grams of aluminum to guess what? Moles of aluminum. Okay, and I'm checking my units, okay, making sure I set it up properly, making sure that they cancel out properly. All right, so if I stop the calculation at this point, the only thing I have is moles of aluminum. Obviously, I gotta get eventually to grams, because way over here, I need to get to grams of iron 2 oxide. Okay, that's where I'm going. So I gotta work my units in that direction. So the next relationship is getting from moles of aluminum to guess what? To moles of iron 2 oxide, iron 2 oxide. Okay, so here's from the balanced chemical equation, the stoichiometric relationship between the iron 2 oxide and aluminum, which is the 3:2. Again, I'm keeping track of my units, making sure things cancel out. So at this point, if I were to stop the calculation and present that answer, I would have my number in units of moles of iron 2 oxide, which is not what we're striving for, because we need to get to grams. So obviously we need to go one more conversion factor, okay? And that one conversion factor, let me clear that up right here. Okay, looking at my units again, moles of iron 2 oxide cancel, moles of iron 2 oxide. So I've gone through here, leaving me behind with units of grams of iron 2 oxide, which is what the question asked for. So now I know by checking my units that I got it set up properly. Okay. And now it's just a matter of you plug it in that number in your calculator. Okay, and you should end up with 22.2 grams of iron 2 oxide. So what does that mean? And go back and think about the question. That means that if I start off with 5.55 grams of aluminum, and I go to the lab and I measure that out, 5.55 grams of aluminum, I need at the minimum, 22.2 grams of iron 2 oxide. Okay, I need that. Notice the ratio there in grams just don't make sense, because you know we're mixing two different moles, right? Even though they share the moles, the units of moles, they could be the same or could be more, but that value, that final number is going to vary depending on the molar mass. Okay, so I need 22.2 grams of iron 2 oxide and 5.55 grams of aluminum for these two to react completely. Now, which brings me to your point. If I were to weigh out 22.1 grams, yes, the reaction will proceed, but not all the aluminum will react, okay? Because there's not enough iron 2 oxide. I need 22.2 grams of iron oxide. And the same token, if I weigh out 22.3 more iron oxide, after the reaction is done, I'm going to have an excess of iron 2 oxide, okay? So you have a little bit of excess. And sometimes you do that. You generally run a reaction with one of these being a little bit in excess to assure that you have maximized all your reactants completely. And then other times you keep the numbers the same because you don't want to contaminate what you're trying to find with other stuff. So A lot of variables involved in chemistry when you're trying to make compounds. All right, second question. You start off with 10.25 grams of aluminum, okay? We were trying to calculate the amount of aluminum oxide, if you recall, okay? So obviously we're gonna convert the aluminum. That's a relationship. We're concerned about the aluminum and aluminum oxide. That's our focus. So first step, like it was in the first part of the question, was we got to convert the grams of aluminum to moles of aluminum. Okay. And like I've been doing, I'm keeping track of my units, making sure things cancel out. At this point, I have moles of aluminum, and now I need to get to moles of what I'm looking for, which is aluminum oxide. So that requires the stoichiometric relationship between the aluminum oxide and the aluminum, which is a 1:2. Okay, and that again comes from the balanced chemical equation. Keeping track of my units, making sure things cancel out. So at this point, I am unit-wise in moles of aluminum oxide. Notice I start off with grams of aluminum, went to moles of aluminum. Now I'm in moles of aluminum oxide. Now I can convert to grams of aluminum oxide because I need one more conversion factor, which is the molar mass of aluminum oxide. And I get that to refresh your memory. There's 2 aluminums, 3 oxygens. I tally up the atomic mass of each one, 2 aluminums and 3 oxygens, tally it up. That should add up to be 101.96 grams per mole. Okay, check your units as you're really doing the math. Now, unit-wise, you are where you need to be, and that is in the units of grams of aluminum oxide. I apologize if I sound redundant and I'm repeating it over and over again, and I do that for a reason, because I'm trying to emphasize keeping track of your units, okay? And I'm sure if you got it, perfecto, you're good to go, okay? But if you're still kind of sketchy about it, you know, it sounds like I'm going from apples to oranges, which we are. We are magically going from apples to oranges, but we're not doing magically. We're having factors in there to get us to apples to oranges. Okay. All right. So then finally, that adds up to calories up to 19.37 grams of aluminum. So if to visualize this, if you will, if you weigh out 10.25 grams of aluminum metal, and you have a little bit of excess, so you can calculate how much iron oxide you need, just like we did in the first step. But for that amount, you're probably going to need, you know, a little bit, almost twice. See, if you started off with 10.25 grams of aluminum, in question number 1, you were at 5.55, which is about, you know, twice that. You're probably going to need around 44-ish grams of iron 2 oxide. Anyway, you'll have 10.25 grams of aluminum. You run the reaction, and when you're done, you should have 19.35 grams of aluminum oxide. Okay, and this, by the way, is what we call the theoretical yield. You know, what this means is this. Okay, theoretically, if I start off with 10.25 grams of aluminum oxide and enough iron 2 oxide, I should make 19.375 grams of aluminum oxide. And that is what we call our theoretical yield. It's a little side note here. But you may have this in the lab, okay? But in reality, nothing's 100%. I always state that. Nothing's 100%. And so in reality, you may not weigh out exactly 19.37 grams of aluminum oxide. You might maybe weigh out 10 grams. So what we do is we take the 10 grams of actual and divide it by our theoretical, which is 19.37 grams times our 100, and that calculates what we call percent yield. And very rarely do you find reactions that are, 100% yield. If there is, you're skeptical, it's probably contaminated. But on the average, good 10, 80, 90% is good. Okay. So your actual, which you actually weigh out, divided by your TY theoretical yield, which you calculate like we did here, times 100 gives you the percent yield. Okay. All right. That percent yield is very crucial, especially in the industry. A friend of mine used to work for Pittsburgh Paint and Glass, PP&G, as a chemist. They make the material that some of you may have some glasses that turn dark when the sun hits them. There's a chemical in there that changes configuration once it's hits a UV light. Very expensive material, and he was able to up the percent yield when they manufactured only about 5%, but it created in saving millions and millions of dollars. So you get a nice little bonus check for that. All right. So this flow chart, if you follow this flow chart, this will get you from point A to point B, okay? And then also incorporates the calculations about gases at STP. We call that at STP, 0 degrees Celsius and at 1 atmosphere, okay? A gas occupies a volume, 1 mole of gas occupies a volume of 22.4 liters, okay? But only at STP. Well, the point being here that you can, following this chart, you could be given grams of some reactant and be asked to calculate the volume of a gas that is generated. So I can go from the top left to the bottom left, okay? Or vice versa, okay? Or I could start with grams given and go all the way across to the bottom right where I'm trying to calculate the volume of a gas of some product, or vice versa, okay? Or what we've been doing is the grams given, and we trying to figure out the grams of some material, either reactant or product. Okay. Whatever the direction you can go in both directions here, remember, you have to go through moles, okay, and the mole ratio of the chemical reaction. So you got to convert the grams or the volume that's given to you to moles. And then from the moles given, now from the moles ratio, you can go to moles or whatever you're looking for. And from that point, you can go either to grams of what you're looking for, or the volume of a gas that what you're looking for, if you're at STP. But this flow chart, I highly recommend that when you are, working through the problems, print this flow chart out. Use it to help you. And then, physically mark it and say, okay, the problem says I'm given grams and I need to go to volume because I'm at STP. Okay, so now you can follow the roadmap. Use it as a roadmap to get from point A to point B, okay? All right. All right, well, let's do some word problems. And we're gonna kind of put everything together. All right, so here the question says, write and balance the reaction of hydrochloric acid and solid cobalt, okay? Solid cobalt. Well, this is a very good reaction. Now, they're going to tell you, they have to tell you this because cobalt is not part of the 16, okay? That we would know exactly what its oxidation number would be, what its charge. So they're telling you here that after the reaction's done, cobalt will have a +2 state, okay? That helps you out. You know, where you don't have to guess, because you could, without that bit of information, it'd be difficult to determine which one you're doing, which state it will be in. All right, so let's write down what we have, right? We got cobalt, so cobalt has the formula CO, the symbol of CO, and then we have, which is a solid, right? And then we're going to react HCl. Now, does this, what type of reaction would you say this would be? Does anybody have an idea?
Is it an acid-base reaction?
Not quite, okay, because an acid base, you know, it's a good thought because you got hydrochloric acid and that kind of directs you to an acid base, but there's no base here. There's no hydroxide, okay?
So should it be a single replacement?
You got it, exactly. Single replacement, if you look at the, let me pull up the periodic table here. Okay, if we look at fine cobalt, and remember in the activity series, it's a relative scale, okay? It's not an absolute scale, it's a relative to, specifically to hydrogen. And the ionic form, I should say, the ionic form of hydrogen will be H+, okay? And obviously the atomic form of hydrogen would be H2, the hydrogen gas. So what we're doing is comparing the reactivity of cobalt versus hydrogen, which happens to be in the form of H+, HCl. So we can see here that cobalt is more reactive than hydrogen, okay? And so cobalt is more reactive than hydrogen. So we had wrote down CO plus HCl. And then the next question you ask is the most reactive metal in ionic form. Well, cobalt is more reactive than hydrogen. And no, it's not in reactive form. It is in elemental form. So yes, the reaction proceeds. So what that means is that this hydrogen, which is in ionic form, gets converted to molecular form, which atomic form, or elemental form, I should say, into H2, okay? Now remember, going back to the periodic table, this will help you out. The activity series. All the metals, starting from magnesium to lead, those guys, and I wrote a general reaction, I called those M double prime. In the presence of HX, which would be an acid, well, we're going to just use HCl. Okay, we're always going to generate the gas plus the metal chloride, whatever that metal is, metal chloride. Okay, for the ones that were in bold, lithium and sodium, and I call that M single prime, the simple fact that they are so reactive, they just react with water violently. So those metals in bold in the presence of water will give you the metal prime hydroxide plus hydrogen gas. Okay. And then if we were to take a pH litmus test on that solution, it would be alkaline because of the metal hydroxide. Okay, so the ones in bold in water give you metal hydroxide plus hydrogen gas, a lot of heat, and that ignites the hydrogen gas and it blows up. The metals starting from magnesium up to lead do not react with metal like the way the ones in bold. They require a little more aggressive conditions, and being more aggressive means they're going to have a little acid to it. And so given the fact that all those metals before H are more reactive than H, they're going to react to give you hydrogen gas and the metal chloride, okay? The other guys above hydrogen, from copper up to gold, they won't react with any acid nor in water. They're very unreactive, okay? They will react, but they require very strong acids and very vigorous conditions. But for Chem 130, no reaction with hydrochloric, any acid or any water, which is a good thing if you got copper plates, copper pipes. You don't want your copper reacting with water, right? Okay, so let's go back to where we were. So that being the case, that means that I got cobalt in the presence of HCl, okay, will react, and they said that the new cobalt will be in the +2 stage. Now we know that the hydrogen will be in hydrogen gas. So we got cobalt solid, aqueous hydrochloric acid, hydrogen gas, and we're going to have, because it's a single replacement, the cobalt will replace the hydrogen, okay? But before we put them together, you write them in ionic form first. We know cobalt is a +2. Why? Because they tell us. You have to be given that bit of information. The chlorides, we know that each one is a -1. Okay, it's a group 7 element, and it will be a -1 when it's ionic. We need 2 of them. Okay, and so that becomes cobalt Cl2, and then if you look at this in the solubility rules, which brings you back to the periodic table, in the solubility rules, you will find that the chlorides are soluble unless they were bonded to those heavy metals. Cobalt is not one of them. So this will be aqueous solution, okay? To balance it, well, here I would, I think if we see that we needed 2 chlorides, well, if we put a 2 in front of HCl, that takes care of our chlorides. And guess what? It also takes care of our hydrogens by default. And so we got 1 cobalt on both sides, 2 hydrogens on both sides, and 2 chlorides on both sides, simply by putting the 2 in front of HCl. So we got a balanced chemical equation, okay? Let me clear up my mess and have the slide come in. All right, so that's what we have. So our relationship is 2 hydrochloric acids per 1 cobalt to give us what would be the name? What would be the name of our species here? If I had to write that out, what would be COCl2's name?
Would it be cobalt 2 chloride?
You got it, exactly. Roman numeral 2 chloride. Because again, it's not part of the 16, and therefore we have to write down the specific oxidation state, which is a +2. Because we were told, well, we were told that. Right there, okay? Chloride. Okay, good. All right, so now we got the balanced chemical equation. And obviously, they're going to give you some questions, right? The obvious next step. So, next question says, how many liters of gas at STP will form if we start off with 5 grams of cobalt? Okay. Now, obviously, we're at STP. Being an STP, that means that we can utilize 22.4 liters per mole. okay? Because we are at STP. Now, the question is how many liters of gas? Obviously, there's only one gas here, and that's hydrogen. So we want to know how many liters of this is formed if we start off with 5 grams of cobalt. So what we're interested in is simply the relationship between cobalt and hydrogen gas. And that's it. Everybody else is assumed to be in the correct amount, and we're not concerned about that. Okay? So we're STP, we know we're at 22.4 liters. Also, we know that we have to convert everything to moles. And so we're gonna need the atomic weight of cobalt, right? Because we're starting with 5 grams and I need to get to moles. And to do that, I need the atomic weight of cobalt. So I can look that up, okay? And it should be, here, we'll present it here. There's 5 grams. We start off with what we need, what we're given. Let me read some stuff here. Be consistent with what I've been telling you in the past here. And so this is what I'm given. I'm also going to write down what I'm looking for so I can keep track of where I'm going. And I want to know how many liters of H2. That is my eventual goal, liters of H2. So I got 5.05 grams of cobalt, okay? I need my conversion of grams of cobalt to moles of cobalt. Grams of cobalt cancel out unit-wise, leaving me with moles of cobalt. Then I look at the balanced chemical equation because my next conversion factor will convert that moles of cobalt to moles of hydrogen. Okay? And it's a simple 1-to-1 relationship. There's 1 mole of hydrogen per 1 mole of cobalt. Keeping track of my units. Okay? So at this point, if I needed to stop the calculations, unit-wise, I would be at units of moles of hydrogen gas. Okay? But the question asks, I got to get to liters. So that means, and that I'm at STP, so I can then utilize that relationship of 22.4 liters per mole. Okay? Now, I could have been asked how many grams of hydrogen would that correspond to. Or instead of using the 22.4 liters per mole, I could have put in the atomic weight or the molar mass of hydrogen gas, and that gives me grams of hydrogen gas, right? But here they're asking for the volume, so I use the 22.4, right? And I plug that in, and I end up at 1.90 liters of hydrogen gas. So essentially is this, another way to look at this is this. If I start off with 5 grams of cobalt in the lab, and then I add a little excess hydrogen, hydrochloric acid, there's going to be bubbling action going on, and it will bubble, and I can collect that bubbles, that gas, and I can measure it. And when I measure it, it's going to be the amount will be like 2 liters, a 2-liter bottle of hydrogen gas. Okay. All right. Same reaction, but a different question. Says if 2.374 liters of hydrogen gas are formed, okay, how many grams of hydrochloric acid reacted at STP? And so my concern now is simply the relationship between the hydrogen gas and the HCl. Okay. And if I ran the reaction and I'm back calculating, I measured out 2.374 liters of hydrogen gas. Well, how many grams of hydrochloric acid must have reacted, okay? Assuming we have enough cobalt for it to react to give you 2.374, okay? All right, so that's a relationship. I mark up the equation so I know where I'm going. Write down what I'm given. Okay, and eventually I want to get to grams of hydrochloric acid. Okay, so that helps me with my mapping of my units to make sure I'm going the right direction. So the first one, since I am at STP, and eventually I need to get to moles, so I utilize the 22.4 liter per mole relationship, okay? Then that gives me, the first one gives me moles of hydrogen gas. I need to get to moles of hydrochloric acid, HCl, okay? Again, all along, I'm canceling my units, make sure I'm doing good so far unit-wise. So at this point, I am in units of moles of hydrochloric acid. Now I just simply need one more conversion factor, and that is the molar mass of hydrochloric acid, right? Because HCl has 35.45 for the chloride, 1.01 grams per mole for the hydrogen. That gives me a total of 36.46 grams of hydrochloric acid per mole of hydrochloric acid, okay? Check my units. They are canceling out, leaving me with units of grams per grams of hydrochloric acid. So all I gotta do now is plug it in the calculator. And you should end up with 7.72 grams of hydrochloric acid. Okay, so 7.72 grams of hydrochloric acid, and this sufficient amount of cobalt in there, which we don't have to worry about because we're not being asked a question about cobalt. Just a question between hydrochloric acid and hydrogen gas. So 2.374 liters of hydrogen gas means that 7.72 grams of hydrochloric acid must have reacted. Okay. Okay, now sig figs. With respect to sig figs, obviously, as I stated before, the atomic weights are not utilized to determine that. Again, why? Because the atomic weights come from whole numbers. They are the average, weighted average of the isotopes of the elements involved. Okay, remember carbon 11, 12, 13, and 14. Those are the atomic mass units per each of the isotopes of carbon. But carbon 12 has the vast majority, most of the carbon exists as carbon 12, so like 98%. So when we average those numbers, normally if you average 11, 12, 13, and 14, your average is a straightforward 12.5, right? But it's a weighted average, so that there's more 12 being formed or exist than the others. So our average for carbon is 12.01 because it's a weighted average of all the isotopes. Being that they're a weighted average of whole numbers means that there is an infinite number of sig figs with respect to atomic weight, so we don't use that. The 2 and the 1 obviously are exact numbers, okay? So we don't, that exact numbers are not utilized in determining sig figs. I mentioned before that the 22.4 is a measurement, okay? And therefore could be a factor in determining your sig figs in your answer. And in this case, it did, okay? Because we're given 4 sig figs, 2.374 liters, but our answer has 3 sig figs. And that is simply because the relationship of 22.4 liters, which is a measurement, has 3 sig figs. Okay, so the answer would only have 3 sig figs. Okay, and yeah, be careful on some of the homework. There's a problem like this, very similar. And you may write 4 sig figs, but the answer is in 3 sig figs, or maybe it's 2 and 3, I forget which one. Okay. And simply because you're using 22.4. Okay. Any questions at this point? Okay, now here, they're giving you a reaction in words, and it's your job here, obviously, to write it into a chemical reaction. So they're telling you here, HCl gas, which you, in this case, notice something in nomenclature, and I've been giving you credit if you go in there and you have, let's say, in the nomenclature quiz, it'll say HCl. We're trying to teach Canvas to, you know, if you type in hydrochloric acid, but they mention gas, Canvas counts it wrong. I've been giving you credit for it. Okay. Because HCl as a gas is hydrogen chloride. But when you mix it in water, it becomes acidic and it becomes hydrochloric acid. Okay. So we got HCl is hydrogen chloride, which is not hydrochloric acid, because there's a difference. This would be like this. This would be in gas form. Okay, HCl AQ would be in aqueous. So this would be hydrogen chloride versus hydrochloric acid. Okay, simply because the different physical states that they're in. Okay, so here they say HCl gas plus oxygen gas. So we can write that down. HCl gas plus oxygen gas, which hopefully by now you know it's diatomic, so it's O2, okay, produces, which is our keyword for the arrow, chlorine gas, which is diatomic Cl2 gas, plus water vapor, which is H2O, water vapor, which means gas. So everybody here is in the gas phase, okay, reactants and products. All right, so next we interpreted what we've been told, okay. Now what we got to do is balance it. So we got HCl, and we got 2 chlorides on the right, 1 on the left. You know, I could do, and I could put a 2 in front of HCl. That takes care of the chlorides, the Cls. That also takes care of the oxygens, the hydrogens, I should say. But then I have 1 oxygen. So what can I do? Any suggestions? Anybody out there suggest what I can do? I'm kind of stuck here, right? What can I do? See the dilemma? I got 2 hydrogens on the left. Okay, so I got 2 hydrogens over here, 2 chlorides over here, 2 oxygens over here. My product size, I got 2 chlorides on the right, 2 hydrogens, but only 1 oxygen. Okay, because I got 2 on the left. What if I put a 2 in front of water? Okay, that would take care of my 2 of oxygens, but then that kicks up my hydrogens to 4, does it not? Okay. Now that means that I got to come over here to the left And I need to kick up my hydrogens to 4. What if I put a 4 in front of HCl? That kicks up my chlorides. So now I got 4 chlorides. Okay. Whatever, come back here and I put a 2 in front of the chlorides. Doesn't that help things, straighten things up? Yeah. So I got 4 hydrogens, 4 chlorides, 2 oxygens. So everybody seems to be okay there. 4 chlorides, that's okay. 4 hydrogens, okay. 2 oxygens, okay. We're balanced. Everybody see how I did that? All right. We are balanced. So let me clear it up. Here we go. Okay. So our stoichiometric relationship is 2 HCl per 1 oxygen. It gives us 2 chlorine and 2 waters. Okay. This, by the way, is not a very nice reaction because you generate a poisonous gas, Cl2. All right, so the question says, how many liters of chlorine can be formed if 3 liters of oxygen react completely at STP? And so our concern is how many liters of chlorine, we're looking at how many liters of chlorine can be formed if 3 liters of oxygen, 3 liters of oxygen reacting completely. So that's our relationship that we're concerned about, is simply the O2 and the Cl2, which is 1 to 2. Okay, so as always, we write down what we're looking for, and we want to figure out how many liters of chlorine at the end. Okay, so we are at STP, so we can use our relationship of 22.4 liters per mole. Okay, and then going to the balanced chemical equation, the stoichiometric relationship between chlorine and oxygen is a 2 to 1. Keeping track of your units now, we're making sure things cancel out. At this point, we are at moles of chlorine. And since we are moles of chlorine, the question asks for liters, we can simply put back in the 22.4 liters per mole. Okay. And double check our units. Okay, units for liters of chlorine gas. Now, can anybody see here a relationship that we could, or can anybody see something here that we can simplify this reaction as far as the calculations are concerned?
Multiply 3 by 22.4 and 22.4 and
Okay.
2.
Well, think about this. Doesn't 22 by 4, don't they cancel each other out?
Oh, right. So then
It's simply the relationship.
3 times
Like,
2.
yeah, and this is only true if you can see this. It's only true when everybody in gas form, gas, and the parties that you're calculating are in the gas form, I should say. Okay, plus you're at STP. Okay, when that's the case, you're at STP, and you got to go from liters to liters. You can see the 22.4 liters cancels out on both sides of the calculation. Therefore, you can simply use the stoichiometric relationship in the reaction between what you're given and what you're trying to find volume wise, okay? But if you don't see it, stick with the 22.4 until you become comfortable. I just want you to make you aware of that. Sometimes in these calculations, there are shortcuts, but you have to be aware of why you can make those shortcuts and why it's a legit shortcut, okay? All right. Try these at home. So carbon reaction, in fact, we'll do this now. Hey, tell you what, let's take well, let's go ahead and do it. All right, so the question here says carbon reacts with oxygen gas to form carbon monoxide, okay? Carbon, so the reaction's written there. You can see it's carbon plus oxygen gives us carbon monoxide. Okay. Now the question is how many liters of carbon monoxide at STP can be made from 15 grams of carbon for the first one? So they're asking you about the relationship of carbon with carbon monoxide. We're at STP, which means we can utilize the 22.4 liters per mole relationship. And everything's balanced. You got two carbons, two oxygens, we're good to go. So we're given 15 grams of carbon. We need the atomic weight of carbon to give us moles of carbon. So that's the first factor. The stoichiometric relationship between carbon and carbon monoxide is 2 to 2, or simply 1 to 1. Okay. And then we multiply by the 22.4 liters and we end up with 28.0 liters of carbon. So if you start off with 15 grams of carbon, you undergo this reaction in the presence of oxygen, you will generate 28 liters of carbon monoxide. Okay. The second part says how many liters of carbon monoxide are formed if you start off with 20 liters of oxygen gas. So we're only concerned about the oxygen. Let me change the color here. We're concerned about oxygen and carbon monoxide, the one in blue. Okay, which is a 1 to 2 relationship. So 20 liters of oxygen is what we're given. We use a 22.4 liter relationship per mole because we are at SDP. That converts us the liters of oxygen to moles of oxygen. Then we use the stoichiometric relationship between the oxygen and carbon monoxide, which is a 2 to 1. Okay. And then finally, we go back to the 22.4 liters per mole because we're being asked how many liters of carbon monoxide can be made. So that means you make a total of 40 liters of carbon monoxide if you start off with 20.0 liters of oxygen. Okay. So take a look at that. See if you can come up with the same, see if it's clear for you. If not, we can, after we take a short break, we can come back and go over it again. All right, so overview of calculations. The biggest thing here is, where is it at? This flow chart. This flow chart is critical in these calculations to help you get from point A to point B, okay? I would use this to help you out, okay? Eventually, as you become more proficient with examples, you don't need it, but in the beginning, this is your map to get from grams given to volumes, looking for volumes, or grams looking for grams, okay? And so, summarize all this. Come on. Okay. What we've done so far, we've taken the elements, right? We started off with the elements, we learned about the elements, and then we talked about the electronic structure of these elements, okay? And how metals lose electrons and non-metals gain electrons because the driving force was trying to get to the octet. And so when metals lose electrons, the next shell in, the next valence shell in is full with 8 electrons. When non-metals gain electrons, it filled in their valence shell with the magical 8 number, okay? Once we created those ions, then we're able to put them together in the right ratio to form the compounds, whether they be ionic or whether they be covalent. We talked about naming these compounds. We talked about how we have 16 metals that have a known oxidation number and different from all the other metals. And so we don't have to write Roman numerals to name those compounds because we know their oxidation number 100% of the time. All the other metals, we have to either calculate what their oxidation state is or be told what it is, okay? So we went from the elements to compounds, be it ionic or be it covalent. The covalent compounds, when we put them together, we use prefixes, carbon dioxide, carbon monoxide. When it came to ionic compounds, no prefixes, okay? So we got the compounds, and then what's the next step? We start reacting the compounds with each other. There are 6 types of reaction types, okay? Combination reaction, decomposition reaction, acid-base reaction, a single replacement, double replacement, combustion reaction. There's only 6 of them. We talked about balancing them out. And so had a technique to balance the majority of them, but basically balancing or the reactions that we utilize are fairly simple. So sometimes it's quicker just to do a trial and error with respect to the numbers. So the thing about balancing, you may add a coefficient on the product side, and then that drives you to go back to the reactant side to change another coefficient. So you go back and forth until such state that all the elements are balanced as reactants. There's the same number of reactant elements that there is product elements, okay? Those coefficients, those numbers in front of the compounds that we use to balance it, we utilize because that's the stoichiometric relationship between reactants and the stoichiometric relationship between reactants and products, okay? And we can use those ratios, those relationships as a ratio. And depending on the question asked, we can set it up to do calculations, which we've gone through. So that gave us the stoichiometric ratios, okay? Yeah, based on these ratios and these balanced chemical reactions, and now we started doing calculations of reactants, how much reactants we need, okay, or how much products are being generated, or if we need to calculate how much product we need to make, we use the balanced chemical equation to determine that. We talked about the molar mass because the molar mass, using the molar mass, we can go from grams to moles, from moles to grams, okay? We talked about standard temperature and pressure of gases, that only under those conditions, a gas occupies a volume. 1 mole of gas occupies a volume of 22.4 liters. So we can tap into that relationship to help us do calculations, okay? We can't go from point A to point B without going into moles. The common unit is moles. We start off in grams because that's what we do physically in the lab. We weigh things out in grams. We don't weigh things out in moles. So we got to take the grams and convert that to moles of reactant, and then the balanced chemical equation can now get us 2 moles of product, okay? All right, and this, I can't overemphasize, that is the flow chart to help you navigate through all these calculations, okay? So yeah, do definitely refer to it as much as possible. Okay, all right, so that ladies and gentlemen, brings us to the end of chapter 13. And we are done with that chapter. All right, so let me stop here. I'm gonna